Welcome to today's explainer. We're going to break down the absolute battle between standard direct contact voltage probing and the highly advanced world of non-contact near-field metrology. If you do any work with high-speed switching circuits, what we cover today is absolutely going to change how you view your test bench.
Okay, so picture this scenario. You've just powered up a cutting-edge, high-voltage gallium nitride or silicon carbide half-bridge converter. You carefully clip your standard oscilloscope ground lead to the circuit to measure the switching transients, but the very second you look at the scope, the screen just explodes with this severe 112 megahertz ringing, massive false voltage overshoot, and maybe you even get a violently blown trace. You're standing there staring at the damage, wondering, wait, did my circuit design actually fail, or did my probe just lie to me?
Let's dive right into this and get some answers. Here is our roadmap. We're going to logically progress from the high-speed probing problem right into the parasitic physics and circuit loading, cover a terrifying earth-ground short-circuit hazard, and then jump into non-contact near-field solutions and mathematical waveform reconstruction. Starting off with Section 1, the high-speed probing problem. We have to talk about the wide bandgap metrology challenges, because the game has totally changed. The introduction of gallium nitride and silicon carbide devices has radically transformed power electronics. We're talking about devices that operate with incredibly fast transition times, literally under a blistering 20 nanoseconds, and they switch at megahertz frequencies. This generates extreme rates of change in both voltage and current. The massive problem here is that this kind of speed completely exposes the physical and electrical limitations of your traditional silicon-era measurement tools. Moving right along to Section 2, Parasitic Physics and Circuit Loading, we need to technically prove exactly how a standard contact probe destroys your data integrity. To understand why your signals get so distorted, look no further than this number, 200 nanohenries. Standard single-ended voltage probes use those long ground leads terminated with alligator clips, right? Well, a general engineering rule of thumb dictates that you get about 20 nanohenries of parasitic inductance per inch of wire. So, if you're using a standard 10-inch ground lead pigtail, you are introducing a massive 200 nanohenries of parasitic inductance directly into your measurement path. It's like putting a giant speed bump right in the middle of your high-frequency signals. But honestly, the inductance is only half the battle. Standard high-voltage passive probes also inject about 10 to 15 picofarads of capacitive loading straight into your sensitive circuit nodes. This parasitic capacitance actively shifts the resonant frequencies of your gate driver loops and completely detunes your high-frequency snubbers and filters. And worse, at high frequencies, this capacitive reactance causes the input impedance of your probe to drop like a rock. A standard compensated probe can collapse down to roughly 45 ohms of input impedance at the tip. That heavily loads your high-impedance nodes and completely alters the true dynamic behavior of your active circuits. When you connect a grounded passive probe to a high-frequency circuit, you're effectively building a series RLC resonant loop. If you look at the probing transfer function, the absolutely crucial mathematical takeaway is the denominator. When the interaction between that loop inductance and the tip capacitance perfectly cancels out, the real part of the denominator effectively drops to zero. Boom, the circuit hits an undamped resonance. And that creates the severe artificial voltage peaking that does not actually exist in your physical design.
Now, what's really fascinating about this data is how that math translates into real-world performance. Just focus on the top row there for the standard pigtail lead. That 200 nanohenry inductance, combined with the 10 picofarad capacitance, utterly crushes your system bandwidth down to a measly 171 megahertz. And the kicker? It forces a massive 9.17 dB artificial resonant peak, right at 112.54 megahertz. So even if you shelled out for a 500 megahertz oscilloscope, your pigtail lead is essentially acting as an aggressive filter that's injecting severe ringing artifacts into your waveforms. So we've established the data is bad. Let's look at Section 3, the earth-ground short circuit. This is where we elevate the stakes from a simple measurement error to a very real physical safety hazard. Direct galvanic contact probing can create some incredibly severe electrical shock hazards, and it all stems from one fundamental truth about standard test benches. The chassis of a standard bench oscilloscope is tied directly to AC earth ground through the third prong of its power cord. Because that chassis is grounded, the ground clips of your oscilloscope probes are also tied directly to AC earth ground. Think about what happens if you take that ground clip and connect it to a high-voltage floating switching node, like the primary side of a GaN half-bridge. You have just instantly created a direct, low-resistance path straight to earth ground.
This forces massive destructive fault currents right through your test bench. It blows circuit board traces, destroys the probes, damages the internal circuitry of the scope, and obviously presents a very real danger to you. Section 4. Non-contact near-field solutions. Let's pivot away from the dangerous physics of physical contact and embrace the physics of electromagnetic fields. This brilliantly illustrates our two primary weapons in near-field metrology. First, we have magnetic field, or H-field probes. These are shielded loops that couple magnetically via Faraday's law of induction, generating an output voltage that is directly proportional to the time derivative of the current, or di dt. Then we have electric field, or E-field probes. These couple capacitively via displacement current, producing an output voltage proportional to the voltage derivative, or dV dt. The beauty of both? You capture critical circuit behaviors without ever physically touching the node. The core advantages here are just staggering. By completely removing that physical RLC tank from the equation, near-field probes offer zero electrical loading. That means zero capacitive shifting of your filters and zero inductive ground loop ringing. You get completely safe, non-invasive observation of high-voltage switching waveforms, totally eliminating that scary AC earth-ground risk. Plus, you get to perform high-frequency current sensing without the absolute nightmare of lifting component legs, cutting copper traces, or soldering in bulky shunt resistors. You can even mount these probes onto incredibly precise automated scanning mechanisms, effortlessly capturing phase-resolved data just fractions of a millimeter above the PCB. But, there's always a catch, right? Because these near-field probes don't actually touch the circuit, they capture the derivative of the actual fields, not the original time domain waveform itself. This leads us to our final piece of the puzzle. Section 5, Mathematical Waveform Reconstruction. Let's talk about how we get the true signal back. Because those near-field probes are outputting didt or dV/dt derivatives, and because the probes, cables, and amplifiers all possess their own unique frequency responses, you can't just read the voltage straight off the scope. We have to use advanced mathematics to recover the original waveform. Specifically, we use what's called a frequency-dependent complex-valued system probe factor, coupled with frequency domain deconvolution. Let's step through how this actually builds into our final solution. Step 1, you capture the localized field derivative using your completely safe, non-contact near-field probe. Step 2, you apply your complex calibration matrices to account for the probe resonances, path asymmetries, and any cable losses. Finally, step 3, you utilize deconvolution algorithms. Specifically, you run an inverse fast Fourier transform in the frequency domain to mathematically compensate for the derivative coupling. The end result? You recover a perfect, high-fidelity, time-domain switching waveform with absolutely zero physical probing distortion. So I want to leave you with this final provocative thought. The very next time you're measuring a hyper-fast, wide-band gap power stage, and you catch yourself reaching for that long, highly inductive pigtail ground clip, just stop and ask yourself, are you really ready to blindly inject 200 nanohenries of distortion and risk a catastrophic earth-ground short circuit? Or are you ready to finally reconstruct the truth using non-contact near-field metrology? Thank you so much for exploring the physics of high-speed probing with me in today's explainer. Catch you next time.